if we knew exactly the surface we were going to be attaching to every time, then potentially we could do some design around like an interlocking mechanism or something that relies on two pieces coming together. But because we don't know what that surface is going to look like, we have to design around that. And that's part of this project, is understanding on different surfaces how will our adhesives perform based upon how these defects form at the interface and eventually how those defects cause detachment.
Welcome to Diving into the Discourse, the CSUN Conversations podcast where we talk to faculty and staff about the research and projects and how they impact students in the community. I'm your host, Carmen Ramos Chandler, and with me is mechanical engineering professor Jamie Booth. And today, believe it or not, we're going to talk about geckos. Now, Dr. Booth, explain to me where geckos factor in with mechanical engineering.
Yeah, of course. So, my expertise within the field of mechanical engineering is mechanics of materials and structures. So what that means is that I analyze how structures, how components and materials deform under the action of forces when they exist in their environment, and eventually how they maybe fail as well. But the field that I apply that expertise to is bio-inspired materials. So we look to nature for inspiration on how to create new engineering materials. Nature's had a lot more time than us to dream up engineering solutions. So while we've just had a few hundred years of since the Industrial Revolution, nature's had hundreds of millions of years to come up with really intricate and elegant solutions to engineering problems. And that's how that's what we try to study. We study the mechanisms that exist in natural systems to try to create new engineering materials that maybe solve a problem that we haven't had a traditional mechanism to solve in the past.
I will confess, as a kid, I did spend time outside a lot. And lizards and geckos fascinated me because they could go anywhere. I mean, I to this day, you can see them, and they're on a glass window, they're on a screen, they're on a slick surface, slicker than glass. And why I can understand, I mean, as a child, you wondered, how the heck did they do it? Is that what you're looking at?
Well, we build on a lot of great work by biologists, so a lot of that is actually well understood. It's a fairly mature field. People have been studying this problem for about 20 years now. But fundamentally, you're right that the amazing thing about geckos is their ability to climb on almost any surface, on walls and on ceilings, and not just that, but actually the speed at which they do it. And that's a key part of where the engineering relevance comes in, because we're not just interested in the fact that they can stick. It's actually really easy to make things stick together. It's much, much harder to then separate them again and do it in a way that can be done maybe over tens of thousands of cycles. So the beauty of the gecko, the ability of the gecko, is to detach easily when it needs to, basically. So it's able to strongly attach, but then you don't see geckos standing there heaving their hand off of a wall trying to take a step forward. They wouldn't be running very quickly if they were. And so it's the ability to detach easily that's part of the engineering relevance, because the kind of applications that we look at for potential engineering mimics of the gecko's toe pad are things like industrial automation. So where you have components on an assembly line and you need to reliably pick them up, place them down in a different location, and do that hundreds of thousands of times over the course of even just a single day. Or even on skin, things like being able to attach a bandage to skin in a way that's robust and reliable, but then detach easily without pain. And that's kind of the engineering relevance of trying to do what the gecko does.
I can see a bunch of 6, 5, 4, 3-year-olds praying you move faster to the bandage. But this idea of of that rapid detachment, that has applications not just for Spider-Man and the movies. It's got real-world applications beyond the bandage, doesn't it?
Yeah, exactly. And I think that's in the field of biomimicry. I think a lot of the time people, the first thing that they try to do when studying a natural system is to do exactly what the natural system does. So a lot of the early efforts in this field were exactly as you say on can we make gloves for humans to climb, or can we make climbing robots and things like that. But as the field matures, you start to realize where the same principles can be exploited, but in a new application area. And that's where some of the relevance to things like industrial automation and biomedical applications started to come in, I guess.
That sounds, I mean, I can think the biomedical when it comes to surgery, particularly surgery inside the body, which is so precarious as it is now. But if you could use biomedical robots or something like that when you're inside the body doing something serious, and then have something that's easy, that when you're done with the incision, that could be transformative.
Yeah, I think there's already been some applications of this. So I have some collaborators of mine based out of the Leibniz Institute for New Materials in Germany, and they worked on fixing eardrum perforations using these adhesives. So there definitely are biomedical applications that are really interesting and exciting for sure. That's not so much of the realm of what we work on. We study more of the mechanics, but definitely collaborations with folks in the biomedical field are going to be important in the future.
For the mechanical engineering part, I'm thinking of the recent collapse of the bridge in the East Coast, Baltimore.
Yeah.
And they've lost a major transport area. But I could see how if this research progresses enough, the engineers could construct something that could be temporary, that could facilitate the needs of the traffic, while a permanent structure is built using this technology.
Well, that's an interesting thought. I think in those situations, the kind of loads that we're talking about are fairly low relative to what would be required to hold a structure together. So I wouldn't want to say that we could necessarily create buildings or infrastructure with these adhesives, but they absolutely have their engineering relevance when the loads are smaller. For example, picking up objects and things.
I'm thinking in terms of construction, expediting the construction, because you have machines.
Pick and place, pick up objects, put them down. Yeah, absolutely. Yeah.
Tell me about your research and what are you doing in the lab as you study their detachment?
Yeah. So maybe that requires me to. I can take a quick step back and talk about, because I realized I didn't talk about actually how the gecko is able to achieve these extraordinary capabilities. So essentially what the gecko has on its toe pad are hundreds of thousands of these fibers. They're hair-like fibers, although they're smaller than the human hair. And what the gecko is able to use those to do is to essentially get into all of the nooks and crannies that exist on a real-life surface. If you look at a surface close up, there are many peaks and valleys, asperities as we call them, that exist on the micro and the nano scale. And the gecko's fibers are able to navigate those asperities and get super, super close, intimate contact with the surface that it's trying to attach to. And the reason that that's important is because they fundamentally, for adhesion, they utilize intermolecular forces called van der Waals forces. So these forces exist between all surfaces. That's actually why, as you mentioned in the beginning of the conversation, the gecko is able to adhere to such a wide variety of surfaces, because this is not chemistry dependent. The van der Waals forces exist between all surfaces. They're stronger for some surfaces than for others, but they exist. The only problem with them, the reason, for example, that right now I don't perceive them between my hands and they don't cause my hands to stick together, is that they're very, very short-ranged. So you can think of the range of a force when you bring two magnets together, right? You bring them together and they sort of snap together once you get within a certain distance. You can think of these intermolecular forces as behaving in the same way. It's just that that distance is on the molecular scale. So if you can get surfaces close enough together on the molecular scale, you can harness these forces to get the surfaces to stick together. And by the way, also the fibers are key to the detachment as well, because if the gecko moves the fibers in one direction, it attaches strongly, and if it moves them in the opposite direction, it kind of is utilizing a peeling mechanism. We all know that if you want to remove an adhesive, you kind of do a peel. If you're removing a piece of tape, you kind of peel it from the surface. So the gecko is doing that with this fiber structure that allows it to detach easily.
But that does it so quickly.
And it does it so quickly, exactly. Yeah, that's the beauty.
I mean, they scurry. They don't.
Yeah, exactly. Yeah, and so to move to what we study, so we make essentially synthetic versions of surfaces that don't look exactly like the geckos, because we tailor them to the constraints that we have in terms of what we fabricate and also the kind of surfaces that we're trying to attach to. But we have these, what we call micro-pattern surfaces. So surfaces that have arrays of fiber structures that we mold. That's how we actually make the adhesive samples. We mold them and we use them we can use them to pick up and put down objects. And we have instruments in the lab that bring the surface into contact and retract it, and we measure the force that can be held by the adhesive. But crucially to our project, we also visualize what the contact looks like. So if you look at the contact, you essentially see many subcontacts. So we have these fibers on the surface. So when we bring them into contact with their surface, we see contact at the tips of the fibers. We have these subcontacts that form at the fiber tips. And where the mechanical engineering comes in is that the reason that these fibers detach, what essentially controls how much force the fibers can hold, is tiny little cracks at the interface, little defects that behave just like a crack in an engineering component that would cause failure of that engineering component. So when you apply force to the adhesive, when you try to separate it from the surface, or when you hang an object from it, or whatever you're doing, then you see that these little cracks that formed at the interface, they propagate, and then the fibers detach. And it looks like a little kind of, I don't know, like a little game or something. So as you have all of these fibers in contact, and then you separate the surfaces and they pop off randomly. It's like a little pattern, little fireworks display or something like that. And that's really at the heart of this National Science Foundation grant that we have to study these adhesives, is to study what causes that behavior. So what causes the formation of these defects, and then once the defects are there, how do the defects control the strength of the adhesive, how much load that the adhesive can support. And that's the specific niche that we are trying to investigate with this work.
It seems to me those defects are so random, but they must not be to be effective.
Yeah, I mean, so that's the randomness is exactly the interesting part. So essentially, as I mentioned earlier, when you have two surfaces, they have these peaks and valleys, this roughness, this asperities. And so as you bring them together, sometimes a peak hits a valley, or sometimes a peak hits a peak. And that essentially controls how the defects form within the interface, the regions where the interface is together versus not. And that the region where the interface is not together is what we call a defect, so to speak. And And so that's essentially, what we're studying, that defect formation process and then the detachment by the propagation of those defects.
Wow, I'm just trying to figure out. You're right, because it's not like they were made, at this point we're talking the gecko and the surface were not made to match.
Right.
It wasn't like they were intended like a Lego to plug into one another.
Right, exactly.
So it's that dissimilarness that causes a defect that allows them to pull away. Wow. I can see that. Wow. Yeah. How are you using computers? Are you simulate? I mean, are you? Is it all computer simulation? It's real world simulation?
No. So that's a great question. We have essentially a problem like this always requires a variety of approaches, and also I'm more of a theory modeling and simulation type person by training. But I never like to just publish a paper with only the results of simulations and no real-world experiments. So everything that we do in the lab has some experimental component to it. So we're doing both. We're making these adhesive samples, we're testing them, we're visualizing the contact, seeing how these little defects are propagating through the interface. And at the same time, we're simulating that process in various ways. So we have some of my students work on the simulation of the defect formation, bringing two rough surfaces together. How does the contact form? Some of my students work on computer generating distributions of defects and studying which one would essentially win out to cause detachment, which one is the most damaging to the overall behavior. I have students working on simulations where we actually study how the fibers deform and detach from the surface. So we're really doing a variety of, approaching the problem from a variety of directions. In the end, hopefully, to end up with a full picture of understanding how this phenomena emerges, I guess.
Have you learned it? I know it's only been months, not years and years, but have you learned anything yet, or are you building, we're going to keep pursuing this direction because it looks promising?
Yeah, so I mean, there's a few things. So we have, we've basically been studying where defects are most damaging. So it turns out that if, because our fibers, they have quite an intricate geometry. We call them mushroom shaped because they have this kind of mushroom cap on the end. It looks a little bit like a suction cup, although it's actually not using suction to attach. But turns out that when you have a defect in the interface at the edge, that's very different from a defect that's slightly closer to the center, different from a defect that's right at the center. And so what my students have been working on is kind of mapping out how the strength of the fiber, the strength of attachment, the adhesion, changes as the defect changes size and position within the interface. And we've been able to, or we're starting to be able to use that data to understand how our samples behave in experiment. Because what we can do is actually, when contact forms, we can visualize what the defects look like in experiment. And with our simulations, we know, okay, if a defect is here, it will cause the fiber to have this strength. If a defect is here, it will cause it to have that strength. And so we can actually use the data from modeling to interpret the strength of the adhesive that we observe when we actually do the experiments. So that's been very exciting.
I'm trying to visualize this. So
I should have brought a sample for you to play with. I realized
right.
That was a terrible...
I'm going to be stuck. Does it sound like Velcro?
Our conversation wouldn't continue. You'd just be playing with your adhesive. So,
is it like Velcro when it separates?
That's funny you say that. It does make a very satisfying sound as all of the little fibers pop off. So I always tell my students, or I tell people when they come into the lab, okay, ignore the little tearing sound that you hear every few seconds. Because sometimes we do tests where we do maybe like thousands of cycles, so attach and detach thousands of times repetitively. And if you're sort of in the lab, you can just hear like a little every time the adhesive separates. So I always tell people in the lab, don't be alarmed if you hear this odd sound coming from the corner. It's just our adhesive separating. So it does sound a little bit like that.
At the same time, I'm trying to visualize it because the defects are random. Now the mic can get mad at me. In different places, and these mushroom hair things. I keep thinking of the tiny, the microscopic hair on the gecko, and then they land in, I guess it's the placement. They may land in the center or the side or the edge, depending on where the defect actually happens.
Yeah, so if you think of the mushroom tip as where the contact forms. So you have this sort of like thing that actually kind of look like the moon when we visualize them. And then you have all these, if you think of like the craters on the moon as these little circular randomized objects, those are like our little defects. So we have an overall contact forming and then a kind of distribution of size and position of these flaws in the contact, basically, that we then study.
So it literally is randomness of where that paw, foot of the gecko lands, or with you, it's not like there's a scientifically studied, we need to match things up, because that's not how.
No, it would be great if we knew exactly the surface we were going to be attaching to every time. Then potentially we could do some design around like an interlocking mechanism or something that relies on two pieces coming together. But because we don't know what that surface is going to look like, we have to design around that. And that's part of this project, is understanding on different surfaces how will our adhesives perform based upon how these defects form at the interface and eventually how those defects cause detachment.
Wow. How far along are you before you find the answers to your questions? Now, I know, as a researcher, there are always questions.
Yeah.
Good science, good research leads to more questions.
Absolutely. It's one of the interesting, I think we're very close to understanding it for say one geometry. So we can change the geometry of these fibers that we study. And so every time that geometry changes, the way that the defects behave changes very slightly as well. And so I think the stage of the project that we're at right now is that we have a good understanding of how it might perform for our specific mushroom-shaped design. But the challenge, or also the beauty of this, is that there is such a wide parameter space to be explored of different adhesive designs and how those would interact with opposing surfaces. And that's actually another part of the project that we've started. We've had one cohort already. We have a course-based undergraduate research experience associated with the grant. So what that means is that we're kind of crowdsourcing data while also giving more undergraduate students a chance to participate in research. So that's one of the limitations of a large institution like ours, is that there's only so many opportunities for independent research supervision within the lab of a faculty member. And so one of the areas that I think about in my work is how to expand those opportunities to more undergraduate students, because we know the tremendous benefits that can come from things like retention, and from a perspective of retention and other positive outcomes when students participate in research. So we created a project where in one of our core mechanical engineering classes at the junior year, they're actually doing a research project, but not a toy project. They're really contributing data to our National Science Foundation sponsored effort by performing simulations on different fiber geometries. So essentially what we do is we have some structure around the project, because in the environment of the classroom, you need to have some structure, but every student gets a different geometry of fiber to study.
Mm-hmm.
And they go off, they learn a little bit about the background of the research, they read some papers, they do a little literature review, and then they're on to actually studying the problem of how does my specific geometry of fiber behave. And so they do simulations, and those simulations generate data, and we really use that data. So we're in the process of, we've run one cohort of that. Another couple of cohorts will happen at least before the project is over. And with that, we want to, in the end, what we'll do is we'll collate all of that data and use it to try to better understand, okay, we've done an in-depth investigation on one geometry, this mushroom-shaped geometry. But going outside of that, now we have all of this simulation data from this class project that we can bring together to potentially get a deeper understanding of how the system behaves overall, or how these principles behave overall.
Now, you're looking at the mushroom shape. Are there other geometrical shapes you're looking at besides the mushroom?
Yeah, not just geometrical shapes, but also you can play around with material properties too. So sometimes you can actually have a thin layer of a different material, or you can even change the shape of a different layer of material. So there's many different, I guess you would say, parameters to play with. So in experiment, we just look at the mushroom shape right now, but in simulation, as I mentioned, in this course-based project, we're looking much outside of that because potentially geometries that we have not experimented with in the lab may prove in simulation to be more successful, more robust against these defects, better performing on various surfaces than the ones that we have studied in the lab. And that's the hope of the course-based aspect of that, is to have a broader data set that will allow us to understand that.
Do the students realize in that cohort they may actually be the ones to find the answer?
Well,
that's exciting.
I hope so. I think they're sort of skeptical at first. They're like, oh, this is part of a research project. Like, I'm kind of not forced to be involved with it, but it's part of this project that I have to do for the class. But I think they very quickly are intrigued by it and think it's a fun application. Ultimately, we're still using the same techniques as they're learning in the class. Anyway, that's the technical content of the class. And so I think in the end, they realize it's a fun application of that. And I always tell them, this could turn into a paper. This could be, your name could be on a paper at the end of this project, based upon this crowdsourcing of data. And so I think that's always an exciting prospect for them, that they can kind of contribute to this effort.
But has the response of the students, either in that cohort or in your actual lab, what has it been? Because sometimes when you're doing research, it's all theoretical. And you kind of think about how it can be applied, but even in that instance, it's something very nebulous and very complicated, and we may not it may take 2 or 3 generations before we see any fruition of our research. But this seems within their grasp.
Well, yeah, I mean, that's it's always an easier sell to talking about, for example, when I introduce the project in class, when I can pass around my little demo specimen and students can use it to, it can basically hold a phone is about like the little patches that we create. They're good to pick up and place down a phone. So students
Really?
can put their phone down on the desk. They can kind of place it down, and then they do. So how our fibers work is a little bit different to the geckos. So actually, what we do to detach is we apply a downward compressive force. So you can kind of bring the surface down gently. It's in what we would call the pick operation. So you can pick up your phone and then you place it down and you press down hard on the surface, and the little fibers, they buckle under the weight of that compressive force. And when they buckle, you can actually peel them off easily. So basically, you press down and the sample just pops right off.
Wow.
And so I'm able to pass this sample around to students, and that immediately gets their attention, right? So that then they've seen it work in real life. They know that it's something tangible and interesting to them, and that makes it a way easier sell. I've had situations where I haven't had demos on hand, and I think students kind of think it's this tenuous thing. But when you can really demonstrate how this works, it makes it a lot easier of a sell to say to a student, okay, now go and work on computer simulations.
You're
For a while.
Make it better because you're on the computer.
Yeah, exactly.
Okay, nerd question. Are you picking up on the glass surface or the back of the phone?
Well, that's a great question. So that's part of why this project is important. So right now, our adhesives work really well on smooth surfaces. So on the glass surface, it's actually works really well. If you turn it around, and most phone cases, I think for gripping purposes, have some roughness to them, then the capacity that the adhesive can pick up goes way, way down. And that's all because you have more defects at the interface now because of that surface roughness. So somewhat counterintuitively, you might think a smoother surface is harder to attach to. I think that intuition comes more from friction, because you think that a smooth surface has less friction. And that's true, but we're not actually using friction in our adhesives. And so it's all about getting that close contact to utilize those intermolecular forces. And so that can happen more easily on smooth surfaces than on rough surfaces. And that's because we get on rough surfaces these defects, these big regions where the interface is separated, and that's going to cause early detachment.
So on the rough surfaces, you have more defects.
Yeah, more defects.
And
exactly.
they're also bigger.
Exactly
and
right.
If your mushrooms, I'm going to call them.
Call them mushrooms. Yeah.
If they only have one size, so to speak, they're not magical where they can expand to fit and accommodate to their.
No,
because they're manufactured.
Exactly.
I can see that. I can actually see why that would be harder, because they can't expand to fill that hole the way on the smooth surface of a glass, which also has defects, but they're fewer and smaller.
Yeah. And another thing that's important is how hard you push when you bring the two together, because you can, to a certain extent, close up some of those defects by essentially pressing harder as you bring the two surfaces together. But that only works to a certain extent. And that's one of the things we're also trying to study, is as a function of how hard I press when I bring the two surfaces together, how do the defects change, essentially? So, yeah.
That makes sense, because if you're using your material, the one you're building on, every human has different pressure.
Right.
I'm not going to press down as hard as you do.
Yeah.
And let's just say this has gone to the level where it's in the commercial use. There's no guarantee the same amount of pressure can be applied per individual.
Yeah. Robots are much better at that, but humans, hard to control.
But I can see that, and you want to have more than one application.
Yeah, potentially
for this. I mean, if you go into the biomedical field, you really need to have that variety of pressure, so to speak, because different parts of the body can withstand different parts of pressure. And also the design of the adhesive may be very different depending on the application too. And that's part of why we explore so many different designs, is because, certain designs may perform better on certain roughnesses of surface, or certain compliances of surface is also a big part of it. So glass is a very hard surface, skin is a very soft surface. So and it's malleable. You push up against it. You stretch it, it changes its
Exactly.
texture.
Exactly. Yeah.
Wow.
Yeah. So there's ultimately so many parameters to think about in these systems, and we're just scratching the surface. But yeah, that's part of the larger effort.
Thank you for joining us for diving into the discourse. You can watch and listen to more of our podcasts on the CSUN Conversations website and become part of the CSUN Conversations community.